Good afternoon, everyone. I'm Ira Porwal, and I'm a student of Masters in Technology. I'm currently pursuing MTech IT from International Institute of Professional Studies. And today we'll be seeing the solutions for our end semester examination of the subject Analysis and Design of Algorithm, which is ADA. Uh, so the very first question was of quicksort. So first of all, let us understand what is the idea behind the quicksort and on what basis it works. Like what's the idea and what concept, on what concept does it work. So first, let us understand it by a very basic real life example. Suppose we have a class, suppose there's a class and it has a number of students, and the teacher asks the students to arrange themselves in such a way that the shortest person is at the first position and the tallest one is at the last, which is in the increasing order of their height. So the shortest person, the shortest one in the class, the shortest student in the class already knows that where he actually stands. Similarly, tallest will also know that where he actually have to stand. And in this way, by seeing the shortest person and the tallest person, keeping in reference the middle students arrange themselves accordingly. So that's how the quicksort works, where we have to arrange the elements in such a way that they are in the increasing order, and the shortest one is at the shortest or the smallest element is at the first, and the tallest is at the last. And with the reference to the first and last element, we replace and we arrange. So the quicksort is one of the most popular sorting algorithms, and it is known for its efficiency in sorting larger data sets. In average case, the time complexity of quicksort is O of n log n. The quicksort algorithm follows the divide and conquer approach. जो quicksort algorithm है, ये divide and conquer approach को follow करती है. That we will see further during the explanation. And it works by selecting a pivot element from the data set. Here, if we can see in the example above, we have selected our pivot element as 10. So partitioning the data set around the pivot element and recursively sorting the two resulting sub-arrays. Now here are the steps for the quicksort algorithm. So before seeing the steps, first we will conceptually see that how we will solve it. So here in the example which I'm highlighting, we will keep this example in reference. We will keep this example in reference and see how do we work. So this is the example on which we will be working. On this example, we will be working. So here, as we can see, that we have 10 number of elements. At the position I is 10, 16, 8, 15, 6, 3, 9 and 5, and at the last it's infinity, because the number is not it does not have any limit, so we have considered it as plus infinity. Now we have to arrange these elements in the increasing order, that is shortest or the smallest element will come at the first. But we can see 10 and 16, so they both are not arranged. So first what we will do is we will consider one element as pivot element, and uska reference leke we will solve further elements in the boxes. So first what is the ideal condition for our quicksort is that जो भी एलिमेंट है, वी आर कंसिडरिंग एलिमेंट ई, तो उसके पहले के जो एलिमेंट्स हैं दैट शुड बी स्मॉलर देन, मतलब दैट एंड उसके बाद के जो एलिमेंट्स हैं उससे दैट शुड बी द एलिमेंट शुड बी स्मॉलर देन ई. सो दिस इज़ द आइडियल कंडीशन. जैसे 10 है, हमने इसको ई को हमने बाई चांस 10 माना, तो 10 के पहले वाले सारे एलिमेंट्स 10 से छोटे रहने चाहिए और 10 के बाद वाले एलिमेंट्स 10 से बड़े रहने चाहिए. तो यहाँ पर जैसे 10 और 16, तो ये 10 जो है ये आइडियल कंडीशन में है, इसलिए हमने इसको पाइवट एलिमेंट माना है हमारा, क्योंकि 10 के आगे कुछ नहीं है, लेकिन 10 के बाद जो नंबर है वो उससे बड़ा है, लेकिन हमारे बाकी नंबर्स उस तरीके से अरेंज्ड नहीं है. तो सबसे पहले हमने फर्स्ट पोजीशन पे लिया आई और इधर लिया जे. तो अब हमने देखा कि हमने दोनों एलिमेंट्स को कंपेयर करा। तो सबसे पहले हम लोग 16 से कंपेयर करेंगे 5 को। तो 16 से 5 को कंपेयर करने के लिए हम लोग क्राइटेरिया क्या यूज़ करेंगे, इंक्रीमेंट आई। ये जो हमारा आई है, इसको आई को इंक्रीमेंट करना है अंटिल यू फाइंड एन एलिमेंट ग्रेटर देन 10। तो हम लोग अगर हम आई को इंक्रीमेंट करेंगे जब तक हम लोग एक एलिमेंट ग्रेटर देन 10 नहीं देख लेते। तो हमने 16 देखा, 16 जो है वो ग्रेटर देन 10 है। सिमिलरली हम लास्ट में आते हैं और जे पे देखेंगे। अब जे का हमें उसका अपोजिट देखना है, डिक्रीमेंट जे अंटिल यू फाइंड एन एलिमेंट लेस देन 10। तो 5 जो है वो लेस देन 10 है। तो हम लोग क्या करेंगे, इस 5 को रिप्लेस करेंगे। इस 5 को हम यहाँ पर रिप्लेस करेंगे। हम एक काम करते हैं, यहाँ पर लिख देते हैं 5। यहाँ पर हमने 5 लिखा और ये 5 और ये 16, सॉरी, यहाँ पर हम 16 लिख देंगे। तो ये 5 और 16 को हमने 5 और 16 को हमने रिप्लेस कर दिया, क्योंकि ये हमें पिवट, हमारे पाइवट एलिमेंट्स के जो कंडीशन है इंक्रीमेंट और डिक्रीमेंट वाली, वो मिल गई। फिर हमारा आई यहाँ पर आ जाता है, हमारा आई अब यहाँ पर है। तो अब हम आई पे यहाँ पर आए और अब हम देखेंगे कि जस्ट अ मिनट, हाँ, तो अब हमारा आई यहाँ पर है जो हमने मार्क करके रखा है, और अब हमारा जे जो है वो भी बढ़ गया। तो जे हमारा यहाँ पर आ गया। तो अब ये हमारा जे हो गया। तो अब हमें देखना है आई को, कि आई को इंक्रीमेंट करना है अंटिल यू फाइंड एन एलिमेंट ग्रेटर देन 10। तो अब आई क्या ग्रेटर देन 10 है क्या, नहीं। लेकिन और जे को देखना है, जे को हमें ये देखना है कि अंटिल यू फाइंड एन एलिमेंट लेस देन 10। हाँ, लेकिन जे तो लेस देन 10 है। तो अब हम क्या करेंगे, इनको रिप्लेस कर देंगे। फिर हम यहाँ पर आएंगे 12 और 15 पे, 12 और 15 को रिप्लेस करेंगे। और फिर हम यहाँ पे आएंगे 6 और 3 पे। तो 6 और 3 पे आएंगे तो ये हमारा जे बन जाएगा 6, और 3 जो है वो आई बन जाएगा। तो अब हम इसको रिप्लेस करेंगे 6 और 10 से। तो हमारा पाइवट एलिमेंट यहाँ पर आ जाएगा 10 पे। तो ये वाला जो साइड है हमारा, ये एक एरे बन जाएगा पाइवट एलिमेंट के इस साइड, और एक यहाँ पर एरे बन जाएगा, मतलब यहाँ से यहाँ तक का एक हमारा एक एरे बन जाएगा, और एक हमारा यहाँ से पाइवट एलिमेंट के बाद से एक एरे बन जाएगा यहाँ से यहाँ तक का। फिर इन दोनों को हम लोग सेपरेटली एक दो एरेस की तरह ट्रीट करेंगे और इनमें क्विक सॉर्ट लगाएंगे और इसको सॉर्टिंग के थ्रू सॉल्व करेंगे, और फिर इन दोनों को एक कंबाइन कर देंगे और हमारी क्विक सॉर्ट एल्गोरिदम हो जाएगी। सो दैट्स हाउ वी सॉल्व आवर क्विक सॉर्ट एल्गोरिदम्स, एंड दिस इज़ द कंसेप्ट एंड आइडिया बिहाइंड quick sort. Now let us see stepwise, which we have already mentioned in our presentation. तो अब हम इसका स्टेप वाइज देख लेते हैं कि वी सिलेक्ट द, लेट अस कंसिडर एन एग्जाम्पल। तो हमने यहाँ पर ये एग्जाम्पल कंसिडर करा है 538 42716। तो इसको हम लोग करेंगे, वी सिलेक्ट द लास्ट एलिमेंट ऑफ द एरे। 6 हमने सेलेक्ट कर दिया क्योंकि वो आइडियल कंडीशन में है अपनी, उसके आगे उसका छोटा एलिमेंट है और पीछे कोई है नहीं। फिर वी पार्टीशन द एरे बेस्ड ऑन द पिवट एलिमेंट। द लेफ्ट सब एरे कंसिस्ट 53421 और दूसरा सब एरे करेगा 8 और 7। तो हम इन दोनों एरेस को अकॉर्डिंगली सॉल्व करेंगे, उन दोनों एरेस को सॉर्ट करेंगे और एंड में उन दोनों एरेस को कंबाइन कर देंगे। तो हमारा सॉर्टेड एक एरे आ जाएगा एंड वी कंबाइन द सॉर्टेड एरे, सो वी गेट द आवर डिजायर्ड क्विक सॉर्ट एलिमेंट. So that's how we solve it. And Strasson's matrix multiplication algorithm. So in Strasson's matrix multiplication algorithm is an efficient algorithm for multiplying two matrices, and it works by recursively breaking down the matrices into smaller sub-matrices and using a set of mathematical formulas to compute the product of these sub-matrices. यानी स्ट्रैसन्स मैट्रिक्स मल्टीप्लिकेशन में भी हम लोग मैट्रिक्स, एक बड़ा मैट्रिक्स है उसको 4 या जितने भी इक्वल पार्ट्स में हम लोग डिवाइड कर सकते हैं, करते हैं उनको वी यूज़ सर्टन मैट्रिक्स मैथमेटिकल फॉर्मुलेशंस एंड देन वी सॉल्व दोज मैट्राइसेस सब पार्टीशंस जो हैं एंड वी कंबाइन इट एज अ वन एट द एंड. सो द टाइम कॉम्प्लेक्सिटी ऑफ Strasson's algorithm is O of n power log 2 base 7, which is faster than the traditional matrix multiplication method's time complexity, which is O of n by 3. for large matrices. However, Stressen's algorithm has a larger constant factor in its runtime, which makes it slower than traditional matrix multiplication for smaller matrices. But it also has a drawback. ये faster है and than matrix multiplication, but it has a drawback, as it is that it requires the matrix dimensions to be powers of 2. ये 2 की matrix के जो dimensions है, they should be a power of 2 only. So this means that if the matrices are not in this form, they need to be padded with extra rows and columns, which can be expensive in terms of memory usage. So another drawback of Stressen's algorithm is that it is less numerically stable than traditional matrix multiplication. This means that errors can accumulate during the computation, leading to inaccuracies in the final result. Now, in comparison, traditional matrix multiplication is a simpler and a more straightforward algorithm that is easy to implement and understand. It is also more numerically stable and accurate than Stressen's algorithm. In summary, Stressen's matrix multiplication algorithm is an efficient algorithm for multiplying large matrices, but has some drawbacks, such as its requirements for matrices to be a power of 2 dimensions, lower numerical stability, and a larger constant factor in its runtime. Traditional matrix multiplication, on the other hand, is simpler, more stable, and more accurate, but it is slower for large matrices. The choice of algorithm depends on the specific requirements of the problem and the characteristics of the matrices being multiplied. Now, another question is Prim's algorithm. So Prim's algorithm is a very popular algorithm for finding the minimum spanning tree of a weighted connected graph. So the algorithm works by starting with an arbitrary node and adding the minimum weight edge to the tree until all the nodes are included in the tree. The time complexity of Prim's algorithm is O E log V, where E is the number of edges and V is the number of vertices in the graph. The Prim's algorithm is very useful in a variety of real-world scenarios, such as network routing, transportation planning, and power grid design. For example, it can be used to determine the optimal routes for laying fiber optic cables between cities, or to identify the most efficient routes for shipping goods between the warehouses, because it finds the minimum distance, which we find using minimum spanning trees. So on the other hand, Hamiltonian cycles refer to a cycle that visits every vertex exactly once in a connected graph. Finding a Hamiltonian cycle is known to be an NP-hard problem, meaning that there is no known polynomial time algorithm to solve it. However, there are some approximate algorithms that can find a near optimal Hamiltonian cycle. Hamiltonian cycles have several real-world applications, such as in logistics and transportation planning, where they can be used to find optimal delivery routes between multiple destinations. For example, a delivery company may use a Hamiltonian cycle to find the shortest route that visits all of its customers in a given region. So overall, Prim's algorithm and Hamiltonian cycles are powerful tools in graph theory, which many practical applications in various fields. Also, Prim's algorithm is popular for finding the minimum spanning tree of the weighted connected graph, and Prim's algorithm is very useful. And now overall, Prim's and algorithm and Hamiltonian cycles are more powerful tools in graph theory, with many practical applications in various fields. Now, how to develop a greedy algorithm for sequencing unit time jobs with deadlines and profits? We can follow the following steps. So sort the jobs in the decreasing order of profit. For each job, starting with the highest profit job, schedule the job at the latest possible time slot that is available before the job's deadline. This algorithm is known as deadline scheduling algorithm. The advantage of this approach is that it is easy to implement and has a time complexity O of n log n, where n is the number of jobs. Now, additionally, this algorithm guarantees that we will always find a schedule that achieves the maximum profit. However, there are some limitations to this approach. Firstly, the algorithm assumes that all the jobs have the same unit time. If jobs have different processing times, the algorithm may not find an optimal solution. Secondly, the algorithm assumes that all the jobs have the same deadline. If the jobs have different deadlines, the algorithm may not find an optimal solution. And finally, the algorithm may not work if there are too many jobs with overlapping deadlines. In such a cases, it may not be possible to find a schedule that meets all the deadlines and maximizes the profit. So in summary, the deadline scheduling algorithm is a simple and efficient approach for sequencing unit time jobs and with deadlines and profits. However, it has some limitations and may not always find an optimal solution, especially when the jobs have different processing times and deadlines. Now, the another question if we see is for the Fibonacci series, which is derive time complexity of the iterative recursive versions of the Fibonacci function to compare their efficiency in each case. So the Fibonacci sequence is defined as a series of numbers where each number is the sum of the two preceding numbers, starting with 0 and 1, and then 1 again, then 1 plus 1 2, and so on. So the recursive and iterative versions of the Fibonacci function are the two common ways to compute the nth number in the sequence. So this is how the formula, and this is how we can find. And the time complexity of the recursive version of the Fibonacci function is exponential of O to n part n, where this is because the function makes two recursive calls for each call, and the number of recursive calls grows exponentially with the input size. And this is the iterative version. So the time complexity of the iterative version of the Fibonacci function is linear, which is O of n, and this is because the function iterates through the loop n times, and each iteration takes a constant time. So in terms of efficiency, the iterative version is much faster than the recursive version, and for large input sizes, the exponential time complexity of the recursive version makes it impractical for computing large Fibonacci numbers, whereas the linear time complexity of the iterative version allows it to compute large Fibonacci numbers efficiently. Another question is question number 6, which is explain chain matrix multiplication with a suitable example and discuss its practical applications. तो practical और real life examples हम लोग बोल सकते हैं. So सबसे पहले chain matrix multiplication क्या होता है? It is a technique that involves multiplying several matrices together in a particular order to reduce the total number of operations required. So the order of matrices is important because it affects the number of intermediate products that needed to be computed. Now let us consider the following example of multiplying three matrices A, B and C and see how. So we have taken A as 2 by 2 to 3, B as 3 as to 4, and a C matrix of 4 is to 2. So these are rows and columns 4 and 2. We can compute the product ABC in two different ways. Method 1 is AB, and method 1 would be AB, मतलब जैसे कि A और B को कर दो पहले. तो A और B को कैसे करेंगे? ये जो 3 है, ये 3 और ये 3 कट हो जाएगा, तो ये बन जाएगा 2:4 का मैट्रिक्स, और फिर इसको कर दें 4:2 से, है ना. तो ये बन जाएगा 2:4 और 4:2 करेंगे तो वो 2:2 का मैट्रिक्स बनेगा. फिर दूसरा अगर हम लोग देखें तो पहले B और C को कर दें और फिर A को करें, तो वो A और फिर B C को करें, मतलब साथ में कर दें पहले, तो 2/2 का बनेगा. So in method 1 we first compute the product of matrices A and B with results in a 2/4 matrix. We then multiply intermediate result with the matrix C to obtain the final result A, a 2/2 matrix. Now in method 2 we first compute the product of matrices B and C, which results in a 3:2 matrix. We then multiply this intermediate result with matrix A to obtain the final result, which is 2:2 matrix ही मिलेगा. So the number of operations required to compute the product of the three matrices depends on the method used. In the case method 1 requires 24 scalar multiplications, while method 2 requires 18 scalar multiplications. So we can see method 2 is more efficient since it requires fewer operations. मैट्रिक्स चेन मल्टीप्लिकेशन के जो प्रैक्टिकल या हम बोल सकते हैं रियल लाइफ एग्जांपल्स हैं. सो इन मैनी एरियाज इंक्लूडिंग कंप्यूटर ग्राफिक्स, साइंटिफिक कंप्यूटिंग एंड मशीन लर्निंग. फॉर एग्जांपल, in computer graphics, matrix multiplication is used to transform 3D models and camera views. In scientific computing, matrix multiplication is used to solve system of linear equations and perform numerical simulations. In machine learning, the matrix multiplication is used in neural network computations, such as the dot product between the weight matrix and the input data. By using chained matrix multiplication, we can reduce the number of operations required for these computations, which can lead to faster and more efficient algorithms. The time complexity of chained matrix multiplication depends on the order in which the matrices are multiplied. If we have n matrices, A1, A2 to An, the number of scalar multiplications required to multiply them depends on the order in which they are multiplied. So there are n minus 1 factorial possible orders in which to multiply n matrices. However, only a few of these are optimal, and the most efficient way to multiply the matrices can be found using dynamic programming. Matrix multiplication or matrix chain multiplication, all of these are performed using dynamic programming only, so which reduces the time complexity of it to O of n to the power 3. So the dynamic programming approach. Dynamic programming approach is an efficient approach for solving algorithms and for finding the desired result. So the dynamic programming approach involves computing the optimal costs of multiplying every subsequence of matrices and using these costs to compute the optimal cost of multiplying the entire sequence of matrices. The algorithm involves filling a table with the optimal costs of multiplying every subsequence of matrices. The table is filled diagonally, and the diagonal entries correspond to multiplying a single matrix. The time complexity of the dynamic programming approach is O of n to the power 3, where n is the number of matrices, and this is because we need to fill an n by n table, and each entry requires O of n operations to compute. The time complexity of chained matrix multiplication can have a significant impact on the overall performance of an algorithm that uses this operation, and if the matrices are large and the number of matrices is large, so the time complexity of chained matrix multiplication can dominate over the time complexity of the algorithm. So therefore, it is important to choose an efficient algorithm for chained matrix multiplication, such as we usually use dynamic programming, and additionally techniques such as parallel computing and caching can be used to further optimize the performance of the algorithm. As an AI language model, Now the last question, which is question number 8 ka we will see A part, which is write a non-deterministic search and sort algorithm. So non-deterministic algorithms are the algorithms that can make random choices during their execution, and these algorithms are used in situations where it is difficult or impossible to determine the optimal solution in a reasonable amount of time. One example of a non-deterministic search algorithm is the Monte Carlo tree search algorithm. This algorithm is often used in games and other applications that involve searching large trees of possible moves. The Monte Carlo tree search algorithm randomly selects moves and evaluates their effectiveness based on simulated playthroughs of the game, and this allows the algorithm to focus its search on the most promising moves. Another example of a non-deterministic algorithm is the genetic algorithm, which is often used in optimization problems. This algorithm simulates the process of natural selection by generating a population of candidate solutions and iteratively selecting the fittest solutions to create the next generation. The algorithm makes random choices in the selection and mutation of solutions, allowing it to explore a wide range of possible solutions. The non-deterministic sorting algorithms are the algorithms that use the randomization to sort the data. One example of a non-deterministic sorting algorithm is the BOGO sort algorithm. This algorithm randomly shuffles the data and checks if the data is sorted. If it is not sorted, the algorithm shuffles the data again and repeats the process. So the BOGO sort algorithm has a worst case time complexity of O of factorial n, which makes it impractical for large data sets. However, it is often used for educational purposes because of its simplicity. In general, the non-deterministic algorithms can be useful in situations where deterministic algorithms are not feasible. However, they often have larger time complexity and they can be less predictable in their behavior, which makes them less suitable for certain applications. The part B of question 8, which is the we have to explain about just a minute, classes P, NP, NP complete, NP hard, P and NP. So are the important concepts in computer science and computational theory, complexity theory. So the P. So the class P contains all the decision problems that can be solved in polynomial time by a deterministic algorithm. Polynomial time means that the running time of the algorithm is proportional to the polynomial function of the size of the input. Examples of problems in P include sorting, searching, and graph traversal algorithms. These problems are efficiently solvable and have many real-world applications such as data processing and optimization. The NP class contains all the decision problems for which a yes answer can be verified in polynomial time by a non-deterministic algorithm. Non-deterministic algorithms are hypothetical machines that can make multiple choices simultaneously. Examples of problems in NP include the traveling salesperson problem and the Boolean satisfiability problem. These problems are computationally challenging to solve, but once a solution is proposed, it can be verified efficiently. Many real-world optimization problems such as scheduling and logistics fall into this category. NP hard. The class NP hard contains all the decision problems that are at least as hard as the hardest problems in NP. These problems are not necessarily in NP themselves, but they are considered to be at least as difficult to solve. Examples of NP hard problems include the knapsack problem and the graph coloring problem, and these problems are computationally intractable and do not have efficient algorithms for solving them. The NP complete. The NP complete contains all the decision problems that are in both NP and NP hard, and these problems are considered to be the most challenging problems in NP, and they are believed to be fundamentally difficult to solve. Examples of NP complete problems include the traveling salesperson problem and the Boolean satisfiability problem. Solving an NP complete problem is polynomially timed would mean that all the problems in NP would be solved efficiently, which is currently believed to be unlikely. In computer science, these complexity classes are important for understanding the time limits of computation and designing efficient algorithms, and they also have many real-world applications, like particularly in optimization problems. For example, the knapsack problem can be used to optimize inventory management, while the traveling salesperson problem can be used to optimize delivery routes for a logistics company. And in summary, the classes P, NP, NP hard, and NP complete represent different levels of computational complexity and have important applications for algorithm design and optimization problems in various fields. So this was the whole discussion of the end semester examination of ADA, which is Analysis and Design of Algorithms. Hope this was helpful for you. Thank you very much for watching the video. Thank you.